case smallest in lexicographical order. So let's just try to understand the problem. Um, so we are having a number n. So for example, n equals to 13 and k equals to 2, and we want to return the case lexicographically smallest integer in the range from 1 to n. So n is also inclusive. Yeah. So for the lexicographical order, so that is 1 and 1 0 and 1 1. Yeah, so it is not like the numerical numbers order 1 2 3. So definitely it is not like that. It is not 1 2 3, and instead it's going to be 1 1 0 and 1 1. If we solve it in brute force, definitely it's going to be on time. So it's going to be 10 to the power of 9. Definitely it didn't work. Yeah. Now we're going to use a mathematical way to solve the problem. Yeah. So we want to find all those numbers, and we're going to use a try to solve the problem. So the try idea is that, so from the beginning we have nothing, and then we're going to have numbers like 1, 2, until 9. So this is just from the beginning. So the try is just a tree structure, and after this 1, we're gonna start to have 0, and we're gonna start have 1 until we have 9. Yeah. So I will not draw from this belongs 2 to 9, but for simplicity, I will just continue drawing from this 0. So from this 0, we're gonna continue to have a 0, 1 until 9. As you can see, it seems this problem can be solved by just counting. We're gonna count the all the possible numbers in this branch or in this branch or from the branch 9, and then we're gonna try to use this kind of idea to solve the problem. Yeah. So if you directly use brute force, it's gonna be 10 to the power of 9 times complexity. It didn't work. So instead, we're gonna use a try structure, and we're gonna use mathematics skills to solve the problem. Yeah. So how can we know from this position? So for example, this is just from the beginning. This is nothing, and then we're gonna start from the first position. It's gonna be this number 1, and we're gonna prepare a current. So the current is gonna equal to 1. So this is our current number. It is 1, and we're gonna prepare the ith number. So I gonna equal to 1. So this means for the first number, it is 1, right? So this is 1, this is the first number. So I means for the ith number, for the first number, current means it is the current number. So yeah, so this means if I equal to 1, this means if n equal to 1, so we're gonna directly return a 1, because k equal to 1, it is the first number. Yeah, if I equal to 1, current equal to 1, it means n equal to 1 and k equal to 1, and this is our second example. We're gonna directly return a 1. Yeah, but what happens is this value gonna be a really big value. So for example, this n gonna equal to maybe let's say maybe 113. Yeah, so this is the n, and we're gonna check maybe, yeah, we are not sure, maybe k equal to, yeah, we are not sure, maybe k equal to 10 or others. Yeah, this is just an example. But how can we count? Do we know from this number 1 and including its children, how many numbers from this branch 1? And all those numbers should be less than or equal to 113. Yeah, so let's just imagine if we know it, the total number maybe this value is x. Yeah, so the total number is x. If this x is less than and equal to the value k. Yeah, so this means from this number and include this number and all its children, so the value is x. So if this value is, so the total number is x. So if this value is less than and yeah, I think it is less than k. It is not less than equal. So if it is less than k, yeah, so this means the next number must from this number 2, not from this number 1. Yeah, so for example, k equal to 10, but from here we only count a 9. So this means from the 10th number, it's going to be this number 2. It's going to be jumped to the next. So another way is if this k is 10, and our code maybe it is 12. It is more than 10. It is more than and equal than 10. So it must be inside this tree, inside this tree from this number 1. So definitely there are two directions. We can go to the right, or we can go down, continue to check. We just need to use this kind of algorithm to count which direction we're gonna go. If we go to the right, this means the current number from the previously the current number, it is the current number, and then it gonna go to the next. So the current gonna plus a 1, so it gonna become a 2. Otherwise, so the current is gonna times a 10. So from here, this is 0. Actually, this is a 1 0. It is a 10, and this is 1 1, and this is a 1 9. Yeah. So if it go to the right, so this current is gonna plus a 1. If it go down, so this means the current is gonna times a 10. So it's gonna become 10, and then it is 11. But the hard problem is that how can we count it? So for example, n equals to 113. How can we count it? So this is a 1. So if we want to go to the next number, so this is a 2. Yeah. So we're gonna use this number 2 as our border. We're gonna use this border to count it. So this is the border. So from 1 to 2, it means 2 minus 1. We have 1 number, and for here, we're gonna use instead of 2. So here we're gonna use 20. Yeah. So here it means 2 times 10. It's gonna become 20. So yeah. Yeah, let me think about it. Yeah, so this means 20 minus 10. So this is a 10. 20 minus 10, it means from here, we still have 10 numbers. Yeah, so from here we have a number of 1. This is our count. And from here we have a number like 10 to something 19. So it's going to be 10 numbers. And then we're going to go to the next level. But we cannot choose the next level. We cannot choose. So for the next level, actually we can choose 100. Yeah, let me just remove a little bit. Yeah, so from the next level here, actually this is 100. Yeah, so what about this one? So this is 20. So from here, it's gonna become it's gonna become 200. Yeah, I believe it's gonna become 200. So this is a 20. From here, it's gonna be 199. So because this is 1 and 10, 100, and this is a 100 and 0 until to this bronze. So for this bronze, it's gonna be 199. So for the next number, so we're gonna use 200. So 200 minus 100, definitely we cannot use 200 because our maximum number is 113. So this means we're going to use 113 minus 100, but we need to plus a 1 because it is starting from 100. So actually here it is 114 minus 100, so it is 14. Now we have a count, so it is 1 plus 10 plus 14, it is 25. Because it is 25, 25 is more than 10. Let me just use a better color. Let me just use white. So because this 25 is more than 10, so definitely if we are going to calculate the case largest, if we are going to calculate the case lexicographically smallest integer, it's going to be inside this branch from this one. Yeah. So this means we will not go to the right side. So all those areas will be ignored. So this is why it's going to be really fast. Actually, the time complexity going to be log n. Yeah, log n square, because we're going to use 2 log n. Inside our loop, for the loop, it's going to be log n time. But inside of the loop, there's going to be another log n. So it's going to be log n square. So it's going to be really fast. Yeah, if it will not go to the right side, it means it will go to the left side. But this is 25. 25 is just too big, actually. Yeah, from here actually we count it as 25 because it is too big. So this means from here our I, it means the case last number, so I gonna plus 1, so this means we've already used this one. So from here it means I gonna become 2, so I gonna equal to 2 for this number on 10. So we're gonna start from this number 10, and then we're gonna count from this number 10 how many numbers inside. Yeah, and we're gonna continue to check. So let's just imagine, so this is a 10, and from this 10, we have 10, there's only one number, and we're gonna have like 100. Yeah, so for this 10 we're gonna still count its the tree from this number 10. It's gonna be 11, right? Because 10 is one number, and from here 100 to 109 it's gonna be 10 numbers, so it's gonna be 11 numbers. Yeah, so from here we have 11 numbers, and here we still have a number of 1, so it's gonna be 12. Yeah, so actually this 12 is gonna be more than 10. It means it's gonna be inside of this tree. Actually it means it's gonna be from 0, 1 until 8. This is gonna be our final result. So the final result, maybe let me just try to make it okay. So we're gonna have 1, and we're gonna have 10, and we're gonna have 100, and from here until 101 until 108. So 1, 2, 3. Yeah, I think my calculation may be wrong. Maybe it is 107, maybe 106. Yeah, so maybe 106 it is the case largest number. I will not, because this is 1, 2, 3, and from 1 it's going to be 4, and then from 2 to 6 it's going to be another 5 numbers. 2, 3, 4, 5, 6, another 5 numbers, and this is 4 numbers. So the final number is going to be 107. It's going to be the case largest number if k equal to 10 and n equal to 113. So this is just an example. Now we're gonna start the coding. So the coding gonna be a little bit difficult, but we need to understand the whole process why we're gonna use this kind of method to solve the problem. And then maybe we just need a little bit of practice, and yeah, maybe we just need to have a little bit of practice to solve the problem. I mean, not the first time. Yeah, not the first time. If you come across this problem, definitely you cannot solve it. But after a little bit of practice, maybe if you find the similar problem, definitely you can solve it. So I'm gonna use I and the current from 1 and 1. So I means the ith number, current means the first number, it is 1. I'm gonna prepare a function count. I'm gonna count the current number. So currently I will give a pause because I'm gonna start the main function first. So for the main function, I'm gonna check this I. So if I is less than k, this means we didn't find the case largest number yet, but we need to find it. If we find it, we're gonna jump out of the while loop. So we're gonna check steps. So this means from this current number, we're gonna check the steps. So we're gonna count the current. So if steps plus I, so I means the ith number. Yeah. So if we've already found the ith number, and then we're gonna plus the steps, that means how many numbers. Yeah. So if this is less than, and yeah, let me think about it. If this is less than and equal to k, so this means we need to jump to the next one. So here, why we're gonna use the equal? Because currently we are calculating these steps. Yeah, but for these steps, actually it is already include 1. If these steps already include 1, so normally we don't need to use equal, but for our calculating of this count, it already include the current number, already include a 1, so we're gonna use equal. So we have to understand why we're gonna use this equal. Yeah, let me just explain this. For example, this is 1, this is 0, 1, until 9. And for our code of the current number, so for example, current is 1, we already included this 1, actually, but this I is also included. So this I is the first number, and we're gonna plus another number, but this number already included. It means we already plus 1. If we plus 1, definitely we're gonna use equal. Otherwise, we don't need to use equal. It's gonna always be less. Yeah. So this is just according to how we're gonna write the function. So this is okay if it is less than or equal to k. So it means it is inside this subtree. If it is inside, we're gonna update the current. Yeah, this means it is not inside. Sorry, I did something wrong. We're gonna jump to the right side. We're gonna jump to this number 2. Yeah, because this is too small, so we're gonna jump to the right to check if we can find it inside the next subtree. Maybe it is inside this number 2. Yeah. So how can we jump? So the current gonna plus equal to 1, and the I gonna plus equal to the steps. So in order to jump. Otherwise, so the current gonna times equal to 10, because we will not jump. This means we will go down. So from here we will go down. We will not jump. Yeah, we have so we have two blocks. So one is go to the right side. So one is go down. If we go down, so the current gonna times 10. So the I gonna plus equal 1, because we only used one step. Yeah, so we have to understand this current and this I. So we use one step, it means we're gonna find the next number. So I gonna plus 1. Here, because we jump a lot of steps, so we're gonna use I plus equal to the steps. So finally, if it goes out of the loop, so this means if I equal to k, or if I is more than k, so we're gonna directly return our current number. Now, the difficult part becomes how can we calculate this count. So actually, I've already explained earlier. So for example, this is 1. So this is a 2. 2 minus 1, it is 1. From here, this is a 0. So we're gonna have 20. 2 times 10, it's gonna become 20. So 20 minus 10, it's gonna become 10. So we're gonna use this kind of a solution to solve the count. So for this function count, let's say we're gonna use check the current. If this current is less than or equal to the maximum number n, so we're gonna update the count. But before that, let's just prepare a neighbor. So the neighbor gonna be current plus 1. Yeah. So this neighbor gonna be the next number. So we're gonna use our current plus 1. And we're gonna update the counter. So we're gonna prepare a counter. It's gonna starting from 0. Yeah. So we're gonna update the counter. It's gonna be a minimum of the neighbor. It's gonna be the next number. Yeah. It's neighbor and n plus 1. So this is as I explained earlier. If this is 113, and if this is 100, actually this is 113. Minus 100 plus 1. So this is why we're going to use the minimum of n plus 1 with neighbor. If this is a smaller neighbor, definitely we're going to use a neighbor. So, but if n plus 1 is smaller, because this is 113, and next is going to be 200. So instead of using 200, we're going to use 113. So we're going to use the minimum minus the current number. And then we're gonna update the current, gonna time 10, and the neighbor gonna time 10 as well. So finally, we're gonna update. We're gonna return the count. So this is the entire solution. As you can see, there's not so much coding, but it's gonna be a little bit difficult to understand. As you can see, it works. Now let me just submit it to check if it can pass. As you can see, it passed and it's pretty fast. Now let's analyze a little bit about the time complexity. Yeah, now we can see the whole drawing, what I drawn before. Actually, the whole drawing is about the algorithm. So for the time complexity, for here, this count, as we can see, for the while loop, there's a jump for the count and a neighbor. It's going to be a 10, so it's going to be a log n time. And also for this while loop, I plus equal to a step, and here count times a 10. This is another log n time. Yeah. So here for this steps, actually this is a log n. So for the whole while loop, it is another log n. So it is a log n squared time complexity. So this is going to be the final time complexity for the problem. Thanks for watching. See you next time.